This is the first of several presentations on the interconnection of systems. Many engineering systems are built up of smaller subsystems, and it makes sense that if we could model the subsystems in terms of their input-output behavior, we can then make models of the larger system. For example, an aircraft hydraulic system consists of many individual components, each with their own inputs and outputs. By making models of the components and then connecting the models together, we can make a model of the larger system. But to do this, we need to talk about how to make the interconnections between subsystems. There are several ways to show the interconnections between systems within a larger model. By far, block diagrams are the most popular method. In block diagrams, systems are represented by blocks which contain the transfer functions. Signals are shown as lines connecting the blocks together. The relationship of a signal to a system is indicated by the arrows present. If the arrow on a line points toward a block, it indicates this signal is an input to the block, and if the arrow points away from the block, it indicates that signal is an output of the block. The block diagram at the bottom of the page indicates that X of S is the input to system H of S, and the output of system H of S is signal Z of S, which is the input to system G of S, producing the output Y of S. We've seen block diagrams several times already in this course. In this presentation, I hope to make their use clear to you. Another element that you'll find in block diagrams is the summation block. This is shown as a circle, typically with the summation sign within it. Two or more signals are inputs to this block, and one signal is typically the output. The summation block shown here adds together the signals X of S and Z of S to produce Y of S. So this element represents the equation Y of S equals X of S plus Z of S. Of course, we can inverse Laplace transform this and find Y of t is equal to X of t plus Z of t. So this indicates the signals are added together at each and every time to produce the output signal Y of t. The second case of the summation block, shown here, actually takes the difference between the two input signals. So this says Y of S is equal to X of S minus Z of S. You know which way to take the difference by the presence of the minus sign next to the Z of S input. Sometimes, to eliminate any ambiguity, signals that are to be added together will have a plus sign next to the arrow of their input. If neither a plus nor minus sign appears next to the arrow going into a summation, you can assume that the signal is going in with the plus sign, that is, to be added. What is important to remember when you see a summation block, or a summation block set up as a difference, is that each of these corresponds to an equation. For example, in the case of the first summation we saw, Y of S equals X of S plus Z of S. In this presentation, we'll examine three elementary types of interconnections of systems. The first is the cascade, or series interconnection. The second is the parallel interconnection. And the third is the feedback interconnection. We'll determine equivalent transfer functions for each of these three interconnections. That is, given the subsystem transfer functions, for example h1 and h2 in these block diagrams, we'll find the overall transfer function for the entire system. Let's look first at the cascade interconnection. We have input x of s going into h1 of s, producing output w of s, and that output then becomes the input to h2 of s to produce output y of s. Our goal is to find the transfer function from x of s to y of s. That is the overall system transfer function for this cascade interconnection. So let's write out the equations for each of the blocks. For the h1 block, we have output w of s is equal to h1 of s times the input x of s. And for the h2 block, we have output y of s is equal to h2 of s times w of s. We can then substitute the first equation into the second to eliminate w of s, and we find y of s is equal to h2 of s times h1 of s times x of s. Or, combining the transfer functions together, y of s is equal to h1 of s, h2 of s times x of s. That is, the overall transfer function of the cascade interconnection is h1 of s times h2 of s. Therefore, the transfer function of a cascade interconnection is the product of the individual subsystem transfer functions. In block diagram form, we can represent this as follows. If we have a cascade interconnection of systems h1 of s and h2 of s, that cascade interconnection may be replaced by a single block which consists of h1 of s times h2 of s. These block diagram representations are equivalent. Now let's examine the parallel interconnection. We have signal x of s, which is being presented as an input to both h1 of s and h2 of s. In response to x of s, h1 of s produces output y1 of s, and in response to x of s, h2 of s produces y2 of s. y1 of s and y2 of s are then summed together to produce the output y of s. We wish to find the transfer function between the signal x of s and the output y of s. We will find this by writing the equations for each of the blocks and for the summation. For system h1 of s, we have output y1 of s is equal to h1 of s times input x of s. In a similar fashion, for block h2, we have y2 of s is equal to h2 of s times x of s. And for the summation junction, we have y of s equals y1 of s plus y2 of s. We'll now substitute y1 of s equals h1 of s times x of s, and y2 of s equals h2 of s times x of s into the equation y of s equals y1 of s plus y2 of s to eliminate y1 of s and y2 of s. After a little algebra, we find that y of s is equal to the quantity h1 of s plus h2 of s times x of s. That is, to find the transfer function of a parallel interconnection, we simply add together the subsystem transfer functions. Therefore, we can replace the parallel interconnection of subsystems h1 and h2 by a block consisting of the summation of the two transfer functions, h1 of s plus h2 of s. These are equivalent representations. Now let's tackle the feedback interconnection. We'll see feedback interconnections quite a bit in this course. We'll have two presentations that will feature them prominently. The input signal to this interconnection is x of s, and the output is y of s. A signal E of s is formed by subtracting z of s from x of s at the summation junction. E of s is the input to system G of s. The output of G of s is y of s. Y of s is also fed as an input to system H of s, which produces its output z of s. The signal z of s is referred to as the feedback signal, and since it is subtracted from x of s to produce E of s, this is referred to as negative feedback. The manner in which output signal y of s is brought back to a summation junction in front of G of s is referred to as the feedback loop. We'll now write the equations for each of the parts of this interconnection. For system G of s, we have y of s is equal to G of s times E of s. For system H of s, we have z of s equals H of s times y of s. And for the summation junction, we have E of s equals x of s minus z of s. We can now do algebra on these three equations to eliminate the internal signals E of s and z of s. This will give us the relationship between y of s and the input x of s. After performing this algebra, we find that the transfer function between input x of s and output y of s is g of s over 1 plus g of s times h of s. This is referred to as the closed loop transfer function. Therefore, the feedback interconnection that we had is equivalent to the block diagram shown here, with x of s as the input and y of s as the output, and g of s over 1 plus g of s h of s as the transfer function. This process of eliminating the feedback loop via the algebra is referred to as loop reduction or collapsing the loop. We just obtained the equivalent transfer function for a negative feedback loop. What about a positive feedback loop? We can go through the exact same process, and we'll find out that the equivalent transfer function for this arrangement is g of s over 1 minus g of s h of s. It's the same result as we've had before, except the denominator has changed from 1 plus g of s h of s to 1 minus g of s h of s. Sometimes we'll encounter very complex system interconnections where multiple things are going on, and then we go through a process to simplify them. This process is known as block diagram reduction, and it's nothing more than doing algebra, except we're doing it graphically. So let's look at an example here. We have the following system. You can see there are items in parallel, there are items in cascade, and there's a feedback loop as well. In block diagram reduction, we'll work on the insides of feedback loops before we try to close them. We'll treat this block diagram reduction as a four-step process. In step 1, we'll find an equivalent transfer function for systems G and H in parallel. In step 2, we'll combine the transfer function that we found in step 1 with the transfer function P in a cascade interconnection. In step 3, we'll combine the two transfer functions in the feedback loop. These are in a cascade interconnection. Finally, in step 4, we'll collapse the feedback loop to find the transfer function between input X and output Y. We'll use the results that we discussed in this presentation. For step 1, the parallel interconnection of G and H is equivalent to the transfer function G plus H. For step 2, the cascade interconnection of G plus H with P is equivalent to quantity G plus H times P. In a similar fashion, the cascade interconnection of T and N in the feedback loop is equivalent to the transfer function T times N. Finally, in step 4, we need to close the feedback loop. In the forward path is G plus H times P, and in the feedback path is T times N. Using the rule for negative feedback loops, we find that the closed loop transfer function between X and Y is G plus H times P divided by 1 plus G plus H times P times T times N. This transfer function is equivalent to the complex diagram that we began with. On this page, you'll find several other block diagram transformations beyond those that we have discussed, including moving a pickoff point and moving a summation junction. You may wish to study these, as they're quite helpful in handling more complex block diagram arrangements.
Block diagrams get mad respect. They show dynamics of cause and effects.
It's hard to understand complex diagrams like stereo circuits in your mom's minivan.
In those cases, it's easy to show how the system interconnections really go.
We got inputs, we got outputs, and transfer functions. 3 basic ways that you can bundle.
The first connection is the cascade. The functions in series get multiplied.
Parallel connections, yo, just listen. The system is simplified with basic addition.
Now listen here, son, this is hotter. Please don't run, just be a little smarter.
Negative feedback is the most complex, but pay attention and see what's next.
The best way to explain is an example, something simple that we can handle.
We got this problem as you can see. Find the transfer function X over V.
Make 2 equations and follow along. 1 for Z, 1 for X, then we'll finish the song.
We're going to try and wrap the third case, which is the negative feedback loop, but we found that a little bit too difficult. So instead, we thought we'd just talk it through at the end of it. Did you think about it during our pop quiz?
Block diagrams get mad respect. They show dynamics of
Good.
cause and effects.
So we know from the basic equation that we're given in the book, Lati, B of S over 1 plus B of S times G of S is the equivalent block diagram, or the transfer function X of S over V of S. Well, while we know this, I kind of found it difficult to really visualize what was going on to get that result. So we thought it would be helpful to break it down to the simplest level and show you how we arrived at this transfer function. We first made an equation, X of S equals Z of S, B of S. From this negative feedback loop, by saying that the input V of S goes into the transfer function B of S and outputs X of S, or Z of S times B of S equals X of S. The second equation we made was to show what Z of S actually is. So we first have V of S, which is coming into the summer on the left side, and then we have the product X of S times G of S, which is just the output of B of S, which goes through this negative feedback loop, G of S, and back into the summer. Make sure you note that it's negative going in here. the next step is just to plug in z of s into equation 1. So we have x of s equals, parentheses, v of s minus x of s, g of s, close parentheses, times b of s. The next step is just simple algebra. So we solve for x of s over v of s to find the exact same transfer function that Lottie described here.
We can't rhyme the rest, it isn't our biz. So think about a tip in this pop quiz.